Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 5, Lesson 6 on the Pythagorean Theorem. Alright, now I know you've seen the Pythagorean Theorem before in middle school math, you maybe even reviewed it in Algebra 1. It's one of the most important ideas in all of math, so let's jump right in it. Alright, the Pythagorean Theorem. Now in middle school you learned how the three sides of any right triangle relate using the Pythagorean Theorem, named after the famed mathematician philosopher Pythagoras, who lived a whopping 2,500 years ago. And by the way, Pythagoras lived so long ago that there's actually a lot of doubt about whether he had anything to do with this theorem whatsoever, or if it just got named for him because maybe somebody that he taught or somebody he taught that taught somebody else actually came up with it. So we don't really know whether Pythagoras invented the Pythagorean theorem or derived it or whatever, but it definitely got named after him. All right, so let's take a look at the Pythagorean theorem. If the legs of a right triangle have lengths of A and B, and the legs are the two sides that are perpendicular to each other, and its hypotenuse has a length of C, that's the one that's not perpendicular, then the three lengths are always related by A squared plus B squared equals C squared. Okay, later on in this course, we're actually going to take a look at where this theorem comes from and we're going to derive it, all right? But that's going to be, I think, in Unit 7, if I recall correctly. For now, we just want to have the theorem so that we can use it to find missing sides of a right triangle. Let's get right into that in exercise number 1. Solve for the missing sides of each right triangle shown below. Now, show your work. Now, when you use the Pythagorean theorem, all right, the first thing that you have to do is decide whether or not you're solving for a missing leg or solving for the hypotenuse. In letter A, we're solving for the hypotenuse. Now, traditionally, the hypotenuse has been called C, all right? But you could call it anything you want. It doesn't really matter as long as you have the relationship correct. So the relationship for the Pythagorean theorem says A squared plus B squared is equal to C squared. So I'm going to say A is 5, I'm going to say B is 12, and I'm going to say C, which is what I'm missing, is just C. Now for a lot of what we do today, you're going to want your calculator to do some numerical work. These I can do so far in my head. 25 plus 144 is C squared. And C squared is 169. All right. Now, you did a lot of work with quadratics in Algebra 1, so this should be no big deal. Obviously, if we've got a variable squared equals a number, the way that we get the variable by itself is we do the inverse of the squaring operation, which is the square root operation. Now, technically, we should get both a positive and a negative result here, but because we're talking about the lengths of a triangle, we're only going to get a positive result. Now 169 is a perfect square, so it's got a nice square root. But if you're not sure, of course, you can always just take out your calculator, either a scientific calculator or a graphing calculator will do in this case, and you use the square root button. In this case, C is 13. All right? Again, make sure that you've got a calculator handy for today. We're going to do at least one or two problems where we're going to get like a kind of a crazy looking decimal here, so it's helpful to have the calculator. Now, in our second case, letter B, right here we've got one of the legs and we've got the hypotenuse, but we're missing the other leg. Should I call it A? Should I call it B? And the answer is it really just doesn't matter. It doesn't. A and B are interchangeable. It's the C, the hypotenuse, that kind of stands alone by itself on one side of the equation. So I tend to like solving for A. So I'm going to call that missing side A. And again, I'm going to just write down the Pythagorean theorem. A squared plus B squared is equal to C squared. So I'm going to get A squared plus 9 squared is equal to 15 squared. That's A squared plus 81 is equal to, I believe, 225, but I like to check this one. 15 squared. 225, excellent. Now, at this point in the other problem, we were able to just take the square root of both sides. Here we have to do a little bit of work, modestly more work. So I just simply need to subtract 81 from both sides. Again, that's going to be easy enough, right? We can just do literally minus 81 on our calculator, and that's going to give us A squared equals 144. And now we take the square root of both sides and we would find A is 12. All right, let me put my calculator away for right now. And let me kind of like bring these up a little bit so you can take a look at that work. All right. Now again, the Pythagorean theorem's main purpose, its main purpose is to allow us to solve for the missing side of a right triangle when we know the other two sides. The only thing that is even slightly tricky about it is the difference between solving for a hypotenuse and solving for one of the two legs, okay? But ultimately speaking, the relationship is always leg squared plus leg squared equals hypotenuse squared. Okay. Now there's a lot of considerations going on here. Because solving for the missing side of a right triangle always involves the taking of square roots, the side lengths can end up being square roots of non-perfect squares. So in the previous exercise, we were finding the square root of 169 at the end, which was 13, and the square root of 144 in the other problem, which was 12. It doesn't always work out nicely. In fact, when we take the square root of a non-perfect square, a good example is 20. 20 is not a perfect square. When we take the square root of 20, we get an answer that's irrational. Now, if you remember something about irrational numbers, they are numbers whose decimals go on forever, they never repeat, they never end, and so ultimately we either have to round them or we have to express them in what's known as simplest radical form, which is going to be the case in exercise 2, and we'll review the process of simplifying a radical within this problem. Let's take a look at exercise number 2. Solve for the missing sides of each right triangle. Express your answers in simplest radical form. Awesome. So yet again, the first thing that we want to do is we want to identify whether we're solving for the hypotenuse or one of the legs. And in letter A, where we have this isosceles right triangle, we've got the two legs, they're 5 each, and we're looking for the hypotenuse. So again, I'm going to call that C, and I'm going to say A squared plus B squared is equal to C squared. That's going to be 5 squared plus 5 squared is equal to C squared. I keep running out of room. Let me extend my page a little bit. I'll get 25 plus 25 is equal to C squared, and C squared is equal to 50. So I'm going to take the square root of both sides. Now, if you are unsure ever whether or not a number is a perfect square or not, 50 is not, but if you're unsure of it, then what you do is you just take your calculator out and you punch in the square root of 50, and you hit enter, and we get this obnoxious number, 7.07106, etc., right? Irrational number, it's going to go on forever. The calculator is only going to show us a certain number of digits, but the number itself goes on forever without ever repeating or no pattern or anything like that. All right, so in this particular problem, because they didn't say give your answer the nearest tenth or the hundredth or whatever, they say simplest radical form, we have to remember exactly what that is. Now, what it means for us to simplify a radical, specifically a square root radical as opposed to a cubed root or anything like that, is we want to find the biggest perfect square that divides into 50, right? So you got these perfect squares, 4, 9, 16, 25, 36, 49, 64, 81, 100, right, etc. Every one of these numbers has a nice square root, right? The square root of 4 is 2, the square root of 9 is 3, the square root of 16 is 4, square root of 25 is 5, etc. down the line. I want the biggest one of these numbers that is a divisor or factor of 50. In this particular case, that's 25. So I can actually break the square root of 50 into the square root of 25 times the square root of 2, and then, as I like to say, take the square root of what you can and leave what you can't. So C ends up being 5 times the square root of 2. Now, why do we have you do this? Well, we have you do this because the state standards in most states ask you to do this. Simplifying radicals really doesn't have a lot of use these days in math or engineering or anything else. If anything, I guess it's to reinforce properties of square roots, but you got to know how to do it. My apologies. I'd much rather have you leave the answer as either the square root of 50 or as some kind of decimal rounded to a certain level of accuracy, but that's just not the case here. All right, so let's take a look at the second part of the problem, letter B. All right, in this case, what we're looking for, right, we've got the hypotenuse of 8. we've got a leg which is 4, and we are missing one of the other legs. So yet again, I'm going to just call that A, because whatever. If you prefer solving for the letter B, I'm good with that too. Anyway, I'm going to call it A. All right. And I'm going to have A squared plus B squared is equal to C squared. I'm going to say A squared plus 4 squared is equal to 8 squared. A squared plus 16 is equal to 64. And just like before when we solved for one of the legs, I'm going to have to subtract before I do my square root. So at this point, I've just got A squared is equal to 48. Awesome, right? So I'm going to take the square root of both sides. And now, just like before, I want to be thinking about which one of these, what is the largest one of these that divides into 48. Now, one thing that's a little bit tricky about 48 is that 4 certainly divides into it. 4 times 12 is 48. Unfortunately, 4 is not the largest perfect square that goes into 48. That distinction happens to be held by the number 16. 16 times 3 is equal to 48. So I can simplify this as the square root of 16 times the square root of 3, and then I'll take the square root of 16, which is 4, and the square root of 3 I can't do much with, so I'll just leave it as the square root of 3. All right, awesome. So simplifying square roots, you got to do it on occasion. Just watch for that phrase, simplest radical form. Write down a list of your perfect squares, see what the largest one is that goes into the number you're taking the square root of, and break it down in this manner. Okay. Now, that's not always the case. Sometimes, right, we're dealing with real-world problems. So right angles arise often in the real world. Because of this, the Pythagorean theorem is extremely useful in many real-world contexts. So let's take a look at one that's kind of a classic, exercise number 3. A 12-foot ladder leans against a wall such that its base is 4 feet from the bottom of the wall as shown. How high up along the wall does the ladder reach? Round your answer to the nearest tenth of a foot. Now, in a problem like this, the natural assumption is that the ground is horizontal and that the wall is vertical, and therefore they make a 90-degree angle with one another. Okay? Thereby, that doesn't look like a right angle symbol, but it was my attempt at it, therefore giving us a right triangle right here. Now we want to know how high up along the wall does the ladder reach, okay? So in other words, we're looking for this particular variable, that height, okay? And we want to round our answer to the nearest tenth of a foot. What I'd like you to do right now is pause the video and see if you can answer this question, find the value of h to the nearest tenth of a foot. All right, well in this case we are looking for one of the legs of the right triangle. We're not looking for the hypotenuse, it's 12. The other leg is 4. So we could say something like, if we wanted to write down the Pythagorean theorem in its original form, a squared plus b squared equals c squared, right? I think I'm going to replace a now with h, b with 4, and c with 12. So I'll get h squared plus 16 is equal to 144. Subtract 16 from both sides. All right, that's going to give me h squared is equal to 128. Take the square root of both sides. Now, a lot of students at this point will start to think about, all right, what do I do in order to get, in order to simplify the square root of 128? Because they're looking to put it in simplest radical form. If they ask you to use the Pythagorean theorem or whatever, they're asking you for an answer to the nearest tenth of a foot, right? Then I'm just going to evaluate it right from here on my calculator. Okay? In other words, I'm going to take my calculator app, I'm going to clear all that out so you can see it a little bit better. I'm going to put in the square root of 128. Enter, and I'm going to get 11.3137, etc. 11.3137, etc. It's an irrational number. They wanted me to round to the nearest tenth of a foot, and therefore my final answer, extend my page a little bit, is h equals 11.3 feet. which is kind of remarkable given that the ladder itself was 12 feet long and we almost reached that high up on the wall, 11.3 feet. Okay. Again, no need to do any kind of simplest radical form on 128, even though it's possible, okay? If they ask you for an answer to the nearest 10th, 100th, or whatever, when you take that square root, just take that square root. Only simplify a radical if they ask you to. Exercise number 4. An equilateral triangle has side lengths of 10 inches each. Determine the area of the triangle in simplest radical form. There it is. Use proper units in your answer. All right, well, before we worry about the area or anything else, let's draw the triangle we're talking about. It's an equilateral triangle, which we know is a triangle that has 3 sides of equal length. And in this case, they're each going to be 10 inches. Okay, great. Now, notice what they're asking us for is the area of the triangle, right? And I'd like to remind you, you are in high school geometry at this point, right? You're supposed to know how to calculate the area of a triangle, and it's 1/2 base times its height, right? Hopefully nobody at this level is thinking it's 1/2 10 times 10, right? That just wouldn't be the case, right? What we need to know in order to figure out the area of this triangle is we've got to know what its height is. Okay, we've got to be able to figure that out. And unfortunately, we got to have it in the simplest radical form because that's what we're looking for the area in. Pause the video now and see if you can figure out what the height of this equilateral triangle is. Well, the real key here is to really cut the equilateral triangle in half, right? And we actually already see half of it, but let me draw it separately, right? We need to find the height based on that right triangle, all right? And that's pretty simple at this point. We've got the hypotenuse, we've got one of the legs. This is actually remarkably similar to exercise 3. We just have to figure out the height in simplest radical form. So I'm going to go right to this step. H squared plus 5 squared is equal to 10 squared. H squared plus 25, I'm going to make that look a little bit more like a 2 and less like just a squiggle, is equal to 100. Whoop. Bye-bye calculator. H squared is equal to 75 when I move the 25 over to the other side. And now H is equal to the square root of 25 times the square root of 3, which is 5 times root 3. All right, so that's the height of my triangle. Now, they didn't ask me for the height, but I did need it in order to calculate the area, which is 1/2 base times height. So let's now write that down. Let me move this out of the way so we have a little bit more room. Right, the area is going to be 1/2 base times height, the base being 10, the height being 5 times root 3. Now keep in mind, you can do multiplication in any order you want because it's both commutative and associative. So for me, I'm going to actually use the associative property of multiplication, and I'm going to do the 1/2 times 10 first. I'm going to choose to do that product first, in which case 1/2 times 10 is 5 times 5 root 3. And now I'm going to choose to do this particular product first. 5 times 5 is 25, and root 3. I just used the associative product of multiplication twice in order to first group the 1/2 times 10, and then to group the 5 times 5, and the root 3 is just lonely. It just kind of hangs out, all right? I do think I need proper units, right? Use proper units in your answer. Since the side lengths are in inches, the area must be in square inches. So let me circle that. That looks like a walrus or something. I don't know what it is. Anyway, the point is the units are square inches. Was that really the point? I don't know. Let's keep going. Let's use the Pythagorean theorem just a little bit more. Our final piece on the Pythagorean theorem is really where we're driving this bus, which is how we're going to use it to find distances in the coordinate plane. We will be using the Pythagorean theorem to calculate the distance in the coordinate plane or lengths of line segments, and those are the same thing. If I'm talking about the distance between 2 points, that is the same as talking about the length of the line segment that connects the 2 points, and that's pretty critical to understand. Now, we can do this because the vertical and horizontal lines are perpendicular to one another. So every grid line that's horizontal is perpendicular to every grid line that's vertical. So let's take a look at finding the length of a line segment or the distance between 2 points in the coordinate plane. Exercise number 5. The line segment shown below has endpoints at A, -2, -1, and B, 4, 7. On the grid, draw a right triangle that has a horizontal leg and a vertical leg, and that has AB as its hypotenuse. Reproduce the right triangle to the right with lengths of both legs marked. Here's what I mean, right? The coordinate grid is very helpful when it comes to things like right triangles and the Pythagorean theorem, because I can draw in this right triangle. All right? That right triangle can be drawn in, right? And in fact, I'd like to reproduce it over here, where again, AB is the hypotenuse of this triangle. And now I can just do some counting. This is 6 units, and this is 8 units. All right, you just kind of count those up if you wanted. And now, of course, we can take a look at letter B. Use the Pythagorean theorem to find the length of AB. This is also the distance from point A to point B. All right, why don't you go ahead and use the Pythagorean theorem to find the length of AB. All right, well in this case, I am looking for the hypotenuse, which I'm pretty much always looking for in this case, because if I'm not, then that means AB must either be vertical or horizontal, and then I don't need to use the Pythagorean theorem at all. So here we go, I'm gonna call that C. Some of you probably already recognize what that's gonna be, but let me put down A squared plus B squared is equal to C squared. All right, we're gonna have 6 squared plus 8 squared is equal to C squared. 36 plus 64 is equal to C squared. 36 plus 64 is 100. So now I'll take the square root of both sides, and C, which is the length of AB, is equal to 10. And that's it. So we can actually find the distance between any 2 points in the coordinate plane by using the Pythagorean theorem. And we're going to devote a lot of time to that in the next lesson. In fact, it's a lesson that we're going to call the distance formula. But let's summarize what we just saw today. Right, what we reviewed today is something that you've been seeing for a couple years now, the Pythagorean theorem. It's one of the oldest, most famous mathematical equations that has ever been discovered in math, right? It's an equation that relates the 3 side lengths of any right triangle, any right triangle. And it basically says if you've got the 2 legs, right, the 2 sides that are perpendicular to each other, if you square them both and add them together, you will always get the squared value of the hypotenuse of the right triangle. This theorem, although it has to do with squaring sides, can then be used if you know 2 lengths or 2 side lengths of a right triangle to find the 3rd length. And that is amazingly useful in math. As long as you stay in math or any technical field like engineering or physics, things like that, you will continue to see the Pythagorean theorem. No matter how far you go, it will keep popping up. All right, so we're going to see it a lot in this course. Make sure to really hammer home on the homework tonight because you want to get the Pythagorean theorem down. For now, I just want to thank you for joining me for another geometry lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.